Hi everyone, welcome back to the Heterogeneous Parallel Programming class. We are at lecture 8.1 and we will be introducing the C++ AMP programming model. The objective of this lecture is to help you to understand the C++ AMP or Accelerator Massive Parallelism programming model. And we're going to go over the basic concepts and constructs, and we'll also be using some simple program examples. The background for C++ AMP is that it's designed to support heterogeneous parallel computing using standard C++ programming tools. For those of you who are familiar with C++, or using C++ programming heavily in your work, this particular interface should be much more friendly to you than the CUDA environment. And it allows you to write GPU computing code or heterogeneous parallel programming parallel code in a generic portable way, and it introduces minimal extension to the C++ language, and that essentially allows you to have very minimal boilerplate code compared to OpenCL. So this is a programming interface that should give you the same level of portability, but at much less tedious the programming environment than OpenCL. So initially, this was developed at Microsoft, and I'd like to especially thank David Callahan, who was formerly at Microsoft, to write that the chapter on C++ AMP in the textbook, and also with his help to help me to understand a lot of the design decisions and trade-offs in C++ AMP. For this course, we need to have a Linux version or implementation of C++ AMP. And currently, the only available C++ AMP implementation is from Multicoreware. And this is actually led by the solution architect, Ray Song, in Champaign, Illinois. And I really appreciate his support and the Multicoreware's willingness to let us use the beta version of the C++ AMP implementation. This is actually not currently available to the general public yet. It's really between alpha and beta release, but we will be able to use this on a kind of an experimental basis to support your simple programming. So if you discover any limitations or bugs, please report that, but also be patient so that our friends at Multicoreware can fix these problems for us. In order for you to understand this lecture, there are a few concepts in C++ that you should be familiar with. And if you're not familiar with these concepts, I would like you to encourage you to go on to the to the internet and learn more about these concepts before you continue this lecture. The first one is using lambda expressions to build functions or as functors. And the second one is using templates for type generic programming. Template programming is used heavily in AMP. And then using the namespaces to control visibility of names, and also using standard template library in some of the kind of the practical use of templates in C++ programming. So here we show a very simple piece of code in C++ AMP. In fact, this is the vector addition, and you will be practicing this piece of code in your lab, and this is an optional lab. So you don't really need to do this lab. In fact, for many students, if your background is strictly in C and or even in Fortran, this lecture is even optional for you. So we are going to start with an include file of amp.h, and then we're going to be using the concurrency namespace. And within the vector function, we have incoming parameters, a, b, c, and n. So we're going to introduce array view for a, b, and c, and we're going to come back to details on this later. We're going to indicate that the c elements, the existing values in C elements are irrelevant or immaterial, that we can throw them away. We don't need, and then we have a function, template function parallel for all that specifies a function that would need to be applied to every element in a data structure. So this corresponds to the kernel function declaration in CUDA. And this function can be declared in place. That is, this function replaces a loop in the original vector add function, but we don't need to declare a separate kernel function. We use the C++ lambda expression here so that the compiler will generate the kernel automatically for us. And then we will do a synchronization to make sure that the kernel execution completes before the function will return with the C value. So here are some important summaries or important explanations of that C++ AMP code. The header file amp.h provides the declaration of the core types and functions, and this is similar to the CUDA.h file. And the second one is the concurrency namespace contains the C++ AMP classes and functions. So this ensures that when you use the names of these functions, they will go to the right classes and functions. And the third one is the template array underscore view or array view, TDAV and so on, provides a multidimensional reference to a C++ array. So if we go back to the syntax, you will see that T is the type of elements. So in our previous example, we have T here for T here, which is float. So we're declared what the type of the elements are float. And we have D is the dimensionality. So in the previous slide, we showed that the dimensionality is one dimension because we're using vectors. And then we have size, which is the number of elements. In the previous example here, AVN, that N is the number of elements in the vector A. And then we have the name. So name in the previous one is A. So with array view float1 AVNA, we essentially specifies that the AB are one-dimensional arrays with n floating point elements. And this is just a new way to access an existing array. So this is actually just a new way to access the incoming parameters A and B. So there's no required memory allocation or copying in this particular specification. So then the array view discard data method indicates that the existing data values in the corresponding array C, in this case, is immaterial. So it will be overwritten with results anyway. So then we can move on to the data parallel kernel specification. The parallel for each function template specifies a computation that will be applied to a collection of values. So this is really the main way for C++ AMP to specify data parallel computation. And the first argument is the C++ AMP extend object specifies the domain of the computation. So in our code example, we use the cv.getInExtent parenthesis function that returns a one-dimensional extent that specifies the domain of element 0 through element n-1 in the vector that will be used in for the data parallel computation. So now, if we go back to the parallel for all line 9 in the code, we see that the first parameter of this function is that extent. So we will get the extent of C. So this is essentially the domain where the elements 0 through n-1 for the C vector. And this computation is going to be done for all those elements. It will be applied to each of these elements in the in C array. And then we have the second argument for that parallel for all function is a C++ function object or functor. So we could have an existing functor in this position, but for C++M, there's a very convenient way for us to create that function in place. That is, we will be, whatever code that we're trying to replace in a existing host code, we actually can build, can just use this the C++ lambda expression to transform that piece of code into a parallel for all construct, and which will be automatically generated into a separate kernel, and there will be kernel invocation that the compiler will arrange so that we don't need to have a separate kernel declaration as we had in the C, in the CUDA and OpenCL situation. So this function is applied to every element in the computation domain. And in our example, the computation domain is all the C elements. And then the leading square bracket equals square bracket is a indication that variables declared in the containing function, which is vector add in this example, but the reference inside the lambda, inside this parallel kernel function, should be captured and copied to the data members of the build function object. So we will be using vectors A, B, and C, which are parameters to the function. So these values will need to be captured and copied to the function, to the build function, and which is essentially the kernel. So the compiler will be implementing the capture activity and copy activity on behalf of you. And then the next part specifies the parameters to the function. And this corresponds to the index, parenthesis index 1i, closing parenthesis part. So the only parameter to the example function is initialized to the location of a thread in the computation domain. So it's that I value. And the I value is actually a global thread index. And remember, there could be up to 3 dimensions of thread index in the CUDA domain. So in this example, we have a template index, which is a short vector up to 3 dimensions of integers, and that correspond to the CUDA global index. In fact, these values correspond to the CUDA expression of block idx.x times block dim.x plus thread idx.x. That familiar indexing expression that we use to be able to cover the entire entire dimension of elements in each dimension. So then finally, in that function header specification, there is a restrict amp modifier. And this is the last part of that function header, and it identifies this function as a device function. It's similar to the CUDA device__device__ keyword. So whenever we apply this modifier to a function, it means that the function will need to be able to be executed on a device. So as a result, these functions need to comply to some restrictions, just very similar to the constraints that we have for CUDA device functions. For example, there can be no reference to global or device variables except static. Actually, it's global or static variables, except when they have a const type and can be reduced to an integer literal value. And that literal value will be transferred to the device. And the second one is variable values should be captured for the lambda expressions, as we have seen for A, B, and C. And then target of function calls may not be virtual methods. So we have to be able to tell exactly which function will be called at compile time. And functions may not be recursively invoked and must be inlined. And this will likely be relaxed in the future. And only the Boolean, integer, unsigned integer, long, unsigned long, float, double, and void may be used at the C++ primitive types. You should not use any other C++ primitive types within these functions. And then no use of dynamic underscore cast, type ID, go to, inline assembly code, try, catch, or throw in these functions. And there are actually more restrictions and more detailed restrictions that are probably not going to apply when you write entry-level basic C++ AMP code. But I'd like to encourage you to look at the specification of C++ AMP for more restrictions. So at this point, you understand all the basic concepts for writing a very simple vector addition code in C++ AMP. If you're interested to learn more about C++ AMP, please read chapter 18.1. Thank you.